Hello there, this is an Algebra 2 video. It is Chapter 7, Section 1, and today we will be talking about graphing exponential functions. Now, like with any function, when you start a new family of functions, it's pretty important and or convenient for you to have some information about what the parent function looks like. You will recall that when we did quadratics, when we did linear functions, you always want to start with the parent function. That kind of gives you an idea of what the function looks like, what its characteristics look like. So an exponential function, first and foremost, has the variable in the exponent. So unlike a polynomial where you have x squared, so the base of the power is the variable and then the exponent is a number. In this case, we have reversed that, and so the base could be anything. Like, for example, what I've graphed here is 2 to the x power. It's the probably most basic exponential that you can graph. 2 to the x power would basically be the base, as long as it's a number greater than 1, qualifies it to be exponential growth. Later we're going to talk about exponential decay, which is why it's important for you to note that. The exponential function is continuous. There's no gaps or holes in it. It's a one-to-one function, so it's going to have an inverse later on. And the function is always increasing. As you can see, as you read the graph from left to right, it's always going in the upward direction, so it's increasing all the time. The domain of the function is going to be all reals. That means that you can plug in any x value, negatives, 0, or positives. The range, however, is the y values that are possible for the function. And as you can see from the graph, the function never dips below the x-axis, and it never actually crosses the x-axis, doesn't touch the x-axis at all. Therefore, the range of this function is any value of y that's positive or basically bigger than 0. So from here on up. That leads us to the asymptote. Exponential functions have an asymptote, which is basically an imaginary boundary that the graph doesn't cross. It's very important that you understand it does not cross. And in this case, the exponential function has an asymptote that is the x-axis. And so it will not go below the x-axis, so you should never draw your graph where it's kind of dipping below that asymptote. And another unique feature of the exponential function is that the intercept is always 0, 1. So that's because if you plug, we already know that to find the intercept, to find the y-intercept, and I should probably clarify this is the y-intercept. The y-intercept, you have to make x equal 0. Well, when you make x equal 0, you're going to get b to the 0 power, and we know that b to, or any number to the 0 power is going to be 1, and therefore it doesn't matter if b was a 2, a 3, or a 4, or a 1/2 raised to the 0 power, it would equal 1. So you're always going to have this issue where it's going to have a y-intercept of 0, 1. So basically, in this case, like I said before, I'm graphing y equals 2 to the x power. So if x is 0, then 2 to the 0 power would be 1. So I'd have my 0, 1. If x is 1, then it would be 2 to the 1 power, which is 2. And so 1, 2, there's my point there. And if x was negative 1, it would be 2 to the negative 1 power. And if you remember negative exponents, that would be 1/2. It would be the reciprocal of that to make it a positive exponent. So here at negative 1, we have 1/2 as our point value. And then I just connected those points with a nice, smooth, continuous curve. And that's how I get my function. And this is your parent graph for exponential growth function. So we're now going to go ahead and graph this function here. It says I'm going to graph y equals 3 to the x power and split the domain and range. So the first thing I want to do is to make a t-table of some values. So I've already chosen some x values here. So 3 to the negative 3 power is basically 1 over 3 to the 3rd power. And 3 to the 3rd power is 27, so it's 1 over 27. That's a very small number. 1 divided by 27 is roughly 0.037. And then when I plug in negative 2, I'm going to get 1 over 3 squared, which is basically 1 over 9. And 1/9 is roughly 0.1 repeating. So 0.1111111. When I plug in 3 to the negative 1 power, it's going to be 1/3. and we know that 1/3 is approximately 0.33, or basically 0.3 repeated. And then we have 0. 3 to the 0 power is 1. 3 to the 1 power is 3, and 3 squared is 9. So basically you need to come up with a table of values, and now I'm just going to plot those values. So -3 is going to be over here, -3, and 0.037 is really close to the x-axis. Remember, it's not going to touch the x-axis, but it's going to be very close to it. At -2, you're going to have 0.1. It's going to be a little bit higher than the 0.03. And then -1 is 0.33 repeating, so it's going to be a little higher than that. And then we're going to have 0, 1, 1, and 1, 2, 3. And our 2, 9 is going to kind of fall off the graph. 5, 6, 7, 8. It's going to be way up here somewhere, but you get the idea. The graph is going something like that. And so it also wants us to state the domain and range. We said earlier that the domain was all reals, and the range for this function is going to be y greater than 0. It's not going to dip below the x-axis there. So that is how you graph this little guy. And so now we're going to ask you to attempt to graph y equals 4 to the x. And then we're going to move on to what always happens when you have parent graphs and functions or a new function is you can also use transformations. We've used transformations to shift quadratics. We've used transformations to shift absolute value. We've used transformations to shift radical functions. And so now we're just going to also include it for exponential functions. So you will see up here the parent graph along with a couple of extra letters. So we have an A, we have an x minus h instead of just the b to the x power, and a k. The h and the k and the a, those are all letters that we've used in the past. So just want to remind you of what they mean. An h is going to be a horizontal transformation. So if you have a plus h, it means you're going to move h units to the left, the parent graph anyway. A minus h is going to move h units to the right. K is a vertical transformation, and so as a plus k, you're going to move k units up. Minus k, k units down. And then, of course, the a is responsible for the orientation and shape of the graph. So orientation meaning that it can flip, just like x squared, when it's positive is like this, and then negative it flips. That's what we mean with the orientation. So we know that the parent graph for an exponential function generally has this kind of a shape. Well, when the a value is negative or less than 0, it's going to have an x-axis reflection. So it's going to actually flip it, and it's going to go in this downward direction. It'll have an x-axis reflection in that case. If the absolute value of the a value is greater than 1, so that's this number here. If there's like a 2 or 3 or 1.5 here, then you're going to have a vertical stretch. So it's just going to mean that the graph is going to stretch out more. And then if you have that value between 0 and 1, so we're not talking about negative, we're talking about 1/2, 1/3, 4/5, any value between 0 and 1, then you're going to have a vertical compression, which means it's going to kind of squeeze it, forcing it to become more flatter. So again, if you were to take this and stretch it, what would happen is it would just kind of look more like this. But if you would compress it, then it would be a bit more wide, because when you compress, it's going to make it like it's going to flatten it out, if you will. So those are just our keys for transformation. So now we're going to use that to graph these functions here. So the first one says to graph the function 2 to the x plus 1. So we already know that 2 to the x has the x-axis as an asymptote. But what's going to happen with this plus 1, that's a k value. So the graph is going to move all up 1 unit, which means that my asymptote is actually going to be here as opposed to the x-axis. So my asymptote is moved up. And so now if I pretend that this is the origin instead of here, then I'm still going to have that 0, 1 business happening. So this will still be 0, 1 here. And then 1, 2, and -1, 1/2. So I'm going to get my graph basically the same graph I had earlier, but it's just shifted 1 unit up. You can even use a t-table if you don't understand quite how to use the transformations. -2 would be 2 to the -2 power plus 1. So 2 to the -2 power would be 1 over 2 squared, which is the same thing as 1/4 plus 1. So it would be 1 1/4. So 1.25. So here's 1, and then 0.25 is going to be up there. -1 would be 1/2 plus 1. So you're going to get 3/2. So that's where your 3/2 is. Sorry, -2 is here. I had the wrong value. So -2 is going to be 1.25. -1 is going to be 1.5. So here at -2 you have 1.25 roughly. 0 is going to be 2, because you're going to get 1 plus 1 is 2. Then you're going to have 2 to the 1 power is 2 plus 1 is 3. So when x is 1, you're going to have 3. And then 2 squared is 4 plus 1 is 5. So when x is 2, you're going to have 5. And I didn't quite graph that guy, but it's right there. So you have the same graph. So you can do it just by moving it up 1 unit, or you can actually do the t-table, however you like to do that. So we're going to do that in part B as well. We have a couple of things going on. The negative is going to tell me that the graph is going to flip. Instead of it being this direction, it's going to go down this direction. The 1/2 also tells me that that number is less than 1. So therefore, this graph is going to have a compression. It's going to be a little bit wider. And then the x minus 2 tells me that it's going to shift 2 units to the right. And so there we go. So I'm going to expect all those things to happen, but we're going to plug in some numbers here. It's really important that you plug things in correctly. We're going to put -1 for the x, so that's going to be -1 minus 2, which is -3. So we're going to go 5 to the -3 power first. And then I'm going to times that by -1/2. Times -1/2. And I get -0.004. And then when I use 0, so I'm going to get -0.004. So that's when x is -1. It's going to be really close to the x-axis, but not quite touching it. And then I'm going to use 0, so I'm going to go 0 minus 2 is -2. So I'm going to go 5 to the -2 power. And then I'm going to times that, which is 0.04, times that by -0.5. And I get -0.02. So just a little bit further than that guy. And then 1, we get 5 to the 1 minus 2, it's 5 to the -1 power. And then times -0.5, we're going to get -0.1. And so I'm trying to get these guys as close as I can to where I want them to be. Okay, and then 2. So we're going to get 5 to the 2 minus 2, that's 0. So 5 to the 0 power is going to be 1, and 1 times -1/2 is -1/2. So the 2 we're going to be right here. So we're going to delete that little guy. So there's -1/2, and then lastly 3. So 5 to the 3 minus 2, 3 minus 2 is 1, so 5 to the 1 power is 5, and then 5 times -1/2 is going to be -2.5. So when x is 3, you're going to be a -2.5, there's -1, -2, -2.5. And so you will see what I'm talking about when I say it's wider. It just takes it a little bit longer to get, it's not as narrow as that one was over there. And that's how you graph that. So now we're going to have you try these two, and then we're going to move on to exponential growth versus exponential decay. So we're not going to do an example of decay, but we are going to do one of growth because they're done in much the same way. There's only one difference between growth and decay. So you have your exponential growth formula. A of t equals a times 1 plus r to the t. You can see that it still has the general form of an exponential function with something to the exponent of t. But when you have a 1 plus r, that's referred to as what we call the growth factor, and 1 minus r is the decay factor. So the only difference in both scenarios, a is the initial amount, r is the percent increase for the time period, and then 1 plus r would be a growth factor, and 1 minus r would be a decay factor. All right, so we're going to apply that to this word problem here. And it says the first U.S. Census was conducted in 1790. At that time, the population was 3,929,214. Since then, the U.S. population has grown by approximately 2.03% annually. Draw a graph showing the population growth of the U.S. since 1790. So what I'm going to do for you is I'm actually going to show you how to write the equation based on the previous slide. I'm not actually going to graph it because you can actually graph this with your calculator. You wouldn't graph it by hand. Those numbers are way too large. But I will tell you what you should make your scale, your window be on your calculator, because otherwise you won't see it, again, because those numbers are so large. But I will show you how to get the equation. So A, we said, was the initial amount. So we have that from our word problem, that A is 3,929,214. The other thing that we need to have is our R value, and R is the percent increase, if you remember, per time period. The time period here is a year. It says annually. So it's going to be 2.03%. But you want to take that number and write it as a percent. So 2.03% means that you move the decimal 2 places over. So you actually get 0.0203 as your R value. So very easily the equation is going to be y equals A, which is 3929214, times 1 plus 0.0203 to the t power, and since 1 plus 0.0203 is just simply 1.0203, you can simplify that even further. 3929214. It is very important, if I haven't already said this before, a lot of times students try to multiply this times that and then get some number to the t power. That would be very, very wrong. You wouldn't want to do that even in the previous examples. So you don't want to take, for example, 1/10 times 6. That would be incorrect, as I didn't take -1/2 times 5, because we have PEMDAS. And PEMDAS tells us to do parentheses and then exponents and then m, which stands for multiplication. So when you take -1/2 times 5, that's m, multiplication. And then if you raise it to the power, that's exponents. So if you do it in that order, you've gone backwards. So you actually want to do exponents first, which is why I kept plugging in 0 minus 2, for example, is -2. I would go 5 to the -2 power, do the exponent thing first, and then get my result and times it by the -1/2. So in a similar fashion, here, you don't want to go 3929214 times 1.0203. You would go 1.0203, raise it to the power, and then multiply it by 3929214 to get your answers. But what I didn't want to tell you is, like I said, we're not going to graph it here on the board, but I did want to give you the scale. You want to go from 0 to 250 on a scale of 25. This is for your calculator window, okay? This is for the X. You want to go from 0 as your minimum to 250 your maximum and a scale of 25. And then you want to go from, for your Y minimum is going to be 0. And your Y maximum is going to be 400 million. It's a big number. And this time you want your scale to be 40 million. Okay, so again, you're going to graph it on your calculator. You want to plug that equation into your calculator. You use this as your max and min for your y, your x and y, and those are for your scale, and then you'll see the same graph that your book will be showing you. All right, so again, with do-it-yourself number 3, you want to do it on the calculator. You still want to set up the equation, but you can go ahead and graph it on the calculator afterwards. All right, so then we're going to go to our parent function again. You recall that in the beginning we started with parent function for growth, exponential growth. Now we're going to go with exponential decay. All right, so in the case of exponential decay, you have the same exact equation here, with the exception that now the b values are between 0 and 1. Okay, and if you remember, if you look at your notes from previous, the beginning of the lesson, we talked about b greater than 1. If b is bigger than 1, then you have an exponential growth function. But if b is between 0 and 1, then you have an exponential decay function. And so here's our parent graph. It looks very much like our other graph. It just appears to have flipped itself on the y-axis. Sometimes we call this a y-axis reflection. And that's because another way of saying this would be for you to have negative exponents. For example, we did 2 to the x, so let's say that we had 1/2 to the x. This qualifies as a decay function because 1/2 is between 0 and 1. But what if we wrote 1/2 as a negative exponent instead of as a fraction? Well, that would be the same thing as 2 to the negative 1 power to the x power. And since we know that a power raised to a power is 2 to the negative x. So we know that when the negative is in front of the equation, that it flips it on the x-axis. We saw that already. Well, now if the negative is in front of the exponent, it flips it on the y-axis. So you have basically a y-axis reflection. And that's not something the book talks about, but I just kind of wanted you to be aware of why that is happening. But at any rate, we have some characteristics of our function here. So it's, again, continuous, still 1 to 1, and now it's always decreasing. This is the only difference between the growth and decay. Before we had it always increasing. You read the graph from left to right, and it was always going up. Now as you read from left to right, it's always going down. So it's always decreasing. Same domain, same range. Asymptote is still the x-axis, and the intercept is still 0, 1. So now we're going to graph these two functions, and then we'll be done with this lesson. So we're going to graph y equals 1/3 to the x power. So I have my t-table here, and I'm going to say 1/3 to the negative 3 power is 27. And then I'm going to say, make sure that you put your 1/3, like your fraction, in parentheses when you do this. And then I'm going to raise it to the negative 2 power. 1/3 raised to the negative 2 is going to be 9. And then 1/3 raised to the negative 1 power is going to be 3. And then 1/3 to the 0 power is going to be 1. 1/3 to the 1 power is 1/3. And 1/3 to the second power is going to be 1/3 squared, which is 1/9. All right, so (1/9) is approximately 0.1, repeating. 1/3 is approximately 0.3, repeating, and everything else is fine. So I'm going to go ahead and not graph the 27 because it's way off my graph here. But starting with negative 2, 9. So here's negative 2. I'm going by 2s here, so I'm going 2, 4, 6, 8, 9. We'll put my little dot there. Then we have negative 1, 3. So 1, 2, and then 3 is going to be right in the middle there. And then we've got 0, 1, which is going to be right here, since we're going by 2s. When x is 1, you're going to get 0.33. So it's going to be really close to my x-axis, but not quite touching it. And you're going to have a graph that looks basically like that. Be very careful that it not go below the x-axis. Remember that there's an asymptote there, so you don't want to dip below that. But that is basically how you graph that little guy. It asks us to say the domain and range. So our domain is all reals, and the range, of course, is y greater than 0. So now we're going to go to part B, and we're going to plug in some values here. We have 2 times 1/4 to the x plus 2 power minus 3. Alright, the first thing I can tell you is that we already know, based on the transformations from before, that this minus 3 is going to shift our graph 3 units down. So we're going by ones here, so 1, 2, 3. So we're going to have our asymptote move from the x-axis at 3 units down. And this x plus 2 is going to shift our graph 2 units to the left. So somewhere over here is going to be my origin now. So that's going to be my point right there. But for those of us that don't know how to read that little guy, we're going to go ahead and do a table. And so we're going to go with -3, -2, -1, 0, 1, 2. Okay? So when I plug in -3, just for the interest of time, when I plug in -3, I get 5. So that means that that's going to be -3 plus 2, which is -1. So that's going to make this 1/4 to the -1 power, which is 4, times 2 is 8, and 8 minus 3 is 5. So again, that's how I'm plugging it in, but in the interest of time, -2 is going to give me -1. -1 is going to give me -2.5. And then 0 is going to be -2.875. 1 is -2.969. So you can see that it's getting closer and closer to 3. And then at 2, it's -2.992. So when I plot those points, -3, 5 is going to be 1, 2, -3, and 5. And -2, -1. Oh, sorry. I did +1 there. -2 is -1. And then -1 is going to be -2.5. -1 into -2.5 is right here. And then 1 is going to be -2.9, so it's going to be really close here. And then finally 2 is going to be even closer, but not quite touching it. So we're going to end up with a graph like that. Alrighty, so just a matter of making a t-table for yourself and making sure that you're plugging in the numbers correctly. So in this case, our domain is still going to be all reals. Nothing happens there. Our range, though, however, has changed because it used to be greater than all the y values were above the x-axis, but now all your y values are above this line here, which is y equals 3. So as long as we have y greater than 3, which reminds me, I'm not sure that I gave you the domain and range of the previous one. Just want to make sure that I did that. I didn't give you the domain and range here. I think I gave the domain and range over there. I'm not sure I did. So domain here should have been all reals. The range, again, like what happened before, is that your asymptote has moved. So now we want y greater than 1 because my asymptote has moved. And then over here, our domain is still all reals. And our range, because now all the y values are below the x-axis, they're not above the x-axis. So you don't want to say y greater than 0, you want to say y less than 0. And I apologize for not having done that earlier, but you want to add that to that example. I just want to make sure that I did it on this one, did do the domain and range on example 1. So now I will give you your do-it-yourself number 4. And once you have completed this example, you will have completed your notes for this lesson. And I will see you in class. And thanks for watching.